Boa tarde, pessoal. Hoje a gente vai dar continuidade ao nosso ciclo de seminários. Hoje nós temos um convidado muito especial, que é o Federico Semeraro. Eu vou começar aqui, o nosso seminário, apresentando o Federico um pouco para vocês. Ele vai apresentar hoje para a gente em inglês, e vou fazer uma breve introdução dele e vou passar a palavra para ele para começarmos a apresentação. Hello, Federico. It's a very nice pleasure to have you here, with us. Federico is here presenting about his work at Artemis Research Center. It's a branch of NASA. He works with development of numerical methods for computing material properties. He has a lot of experience and he has a very nice infrastructure for perform experimental simulations, numerical computations. They developed a very nice software recently, they let the software be available, or it's an open source and for people use for computing material properties. That's very nice because he shares all the developments. And for us, a very nice also, it's a very good, nice pleasure to share knowledge and experience from our side also and from his side. You have, I think, a very nice cooperation. We are established. It's a very nice pleasure to have you here, Federico, and I give the words to you. Thank you again.
Andre. Thank you so much, and thank you everybody for joining. So, as Andre said, my name is Federico, and I'm originally from Italy, but I've been working at NASA Ames Research Center for the past 5 years. I initially joined as an intern doing my master thesis, and then I became a contractor, and I've been working in the thermal protection materials branch as a research scientist. So I've been working on a software that is called the Porous Microstructure Analysis, or PUMA software, and this is what I'm gonna present to you today. And this is, I'm also want to acknowledge, I am part of a group called the Predictive Material Modeling Group, or PMM, and we are funded by a project called the Entry Systems Modeling, which basically looks at thermal protection systems to protect spacecraft re-entering the atmosphere during missions. So the content of my presentation today, I'll introduce the objective of my projects and my software, as well as give a bit of a motivation behind the work in my group. Then I'll jump into the software capabilities, as well as introduce the open source release that we've recently wrapped up. And then I'll focus more on the projects that I've actually myself implemented and have been researching for quite a few years, which deal with the homogenization and characterization of the material properties of the materials we study. And specifically, I'll jump into some of the properties, including the fiber orientation and conductivity, elasticity, and permeability. And finally, I'll give a brief overview of a recent study that my colleagues and I have been working on, which is really the cutting edge type of imaging technique that you can scan these materials with. But let's start with a bit of a motivation. So what my team works on is thermal protection systems, and it's basically, or TPS. And by this, I mean the heat shields that cover basically the outside of the spacecraft. And these are needed for any mission, any planetary mission that has to enter in an atmosphere. And because of the friction with the air or whatever other gas that it encounters in the atmosphere, very high temperatures and stresses are created on the surface of these heat shields. So we need to have basically materials that can handle this type of environments. And so in order to design for such a heat shield, we do a lot of ground-based testing. And here is a brief video of an ArcJet test, which basically, an ArcJet is basically a very high-powered wind tunnel, which actually like throws an extremely high enthalpy flow on the surface of these materials. And you can see them like basically pyrolyze and decompose during the test. And by studying how they react in these environments, we can basically design appropriately the heat shields. However, these type of ArcJet tests cannot exactly mimic the environments that the actual mission is going to experience while re-entering the atmosphere. So in order to do that, actually, we need to do a lot of computational modeling in order to fill the gaps that the ground-based testing cannot mimic. So of course, there are a lot of components that have to be looked at, including like hypersonic CFD or radiation modeling, as well as the actual material response. So my group, specifically the PMM group, looks at this type of modeling, and we tackle it by basically looking at employing a multi-scale approach. So we have software that can mimic the response at the full scale of the heat shield. So we have meshes and we have models basically that mimic the whole surface of these big heat shields, which can be even like meters in size. And however, in order to capture all the complex physics that happens in depth in these materials, we really need to look also at the microscale side of this modeling effort, because we need to compute basically the material properties at the microscale in order to feed them back into the full-scale models. So we have there have been a lot of software that can do the full scale and or material response sides, including I mentioned some of the NASA tools up here, including PATO, Fiat, Char, Icarus. However, Puma, which is the software that I've been working on, is really it's unique in the sense that it's one of the only ones that really looks into the microscale and computes and characterizes the properties at this scale. And the materials that we deal with at NASA for the heat shields, as TPS basically, are some examples are shown in this slide. They're mostly made of carbon fibers, and they're usually also infused with a phenolic phase. And phenolic is basically a resin that as it pyrolyzes, it releases a lot of energy. So it actually basically helps the surface of the heat shield never to reach the very, very high temperatures. But there are multiple different like architectures of these fibers that these fibers can be arranged with. So one of the most typical one is called PICA, or phenolic infused carbon ablator, which is shown in the middle, and it's basically just randomly oriented fibers. However, more recently, NASA has been investigating a lot into arranging these fibers into woven or weaves components, basically by weaving together like in a yarn, as if it was like a fabric. You can actually tailor the material properties to be more performing in a specific direction or in a specific environment. More recently, also, NASA has been doing a lot of research into 3D printing these materials, and this gives even more capability into basically the type of fiber architectures that you can create. So jumping into how do we get basically these microstructures into a computer or virtually digitally? We use a technique called X-ray microtomography, which basically scans a sample, subjects the sample at a very high intensity X-ray, and then you basically take scans at multiple angles, And then there are techniques called tomographic reconstructions, which basically can help you, which enable you to obtain a 3D reconstruction of your model, including the internal, as you can see for this Lego man. So how do they look for X-ray an X-ray microtomography of a TPS? Looks as shown in this case, where you have basically you can see all the way down to the microns scale. If just to give you a sense, like the diameter of one of these fibers is around 8 to 10 micron, and you can even see like up to down to the like hollowed out holes inside the fibers. So this is actually a sub-micron tomographic reconstruction. So what Puma behind the scenes, like how Puma operates, is basically it leverages a class called the workspace, which basically is at the core of every operation that happens on these tomographic samples. And so this workspace class holds the 3D geometry, and then there are multiple classes that we've implemented, like as we were implementing the software to process the 3D domain, which is actually made of voxels, which are 3D pixels. And we've also recently added a lot of like visualization capabilities to the software, but really the core and the most important part of the software lies on the material properties and material response computation. So as I mentioned earlier, a few months ago, we have open sourced the software, and we've really made it as user-friendly as possible. And it can currently be installed using just a single line command, conda install Puma. So we've also added like a lot of documentation and tutorials for new users. And this has boosted, of course, our audience, and anyone that is joining today, like I encourage them to try them themselves. But basically, just to give a bit of an overview of how the software is arranged, Puma used to be years ago implemented only in C++, and it used to be so basically we have the heritage part is still present in the current release. But we've more recently implemented also a Python package, which also calls some of the C++ routines, and we call this Python package PumaPy. And then finally, for whoever doesn't want to use or doesn't want to write lines of codes, basically you can use also like the GUI or graphical user interface, which is shown up here on the top right, where you can still have access to a lot of the capabilities of the software. So to show you a few other snapshots of the GUI, here we are importing a 3D weave from an actual real sample from tomography. And we are showing like a 3D visualization, and finally doing some post-processing of including the weave segmentation of the toes, as well as the detection of the orientation of the toes. So more recently, Puma has also been packaged up as a plugin of a software called Dragonfly. And so that gives us even more visibility into the material science field. And then finally, like I wanted to mention that recently we've been awarded NASA Software of the Year. I've received the news just a couple of months ago, so we're really honored to have been awarded this prize for our efforts. So from now on, I'll jump into more of the capabilities of the software. So a big component are the particle methods that are implemented in Puma. And what these particle methods do is basically like a Monte Carlo type of approach, where you scatter particles throughout your domain and you can compute different properties and do different things. One of the things that the particle method allows you to do is mimic oxidation. So in this case, I'm showing next side by side a sample of fiber form, which is basically just the fiber phase of Pika. And on the right-hand side, there is a 4D tomography, meaning that we actually have a data set of a 3D model changing in time. And on the left is instead a similar domain in Puma. And we can basically mimic the same type of like oxidation of the surface by tweaking the sticking probability of the particles hitting the surface of the model. So again, on the left is a Puma simulation, and on the right is an actual real domain oxidizing on the surface. Then we can also compute the radiative conductivity. The radiative conductivity is very important for high temperatures. And we do this by basically scattering a whole bunch of particles from different spots, and then tracking how far these particles are traveling until they hit the solid surface. And then you can basically do statistics on how far a particle is likely to travel. And that's actually from that estimate, you can actually compute what is called the extinction coefficient, which gives you the radiative conductivity, which is necessary to compute the radiative conductivity. Another thing that we can compute is the tortuosity. So basically, we can basically track how these particles travel through the material, through the microstructure. And by basically checking how tortuous their path is, that's also correlated to the tortuosity at different regimes. And in fact, here you're seeing different Knudsen regimes for different rarefied environments. We can use the particle method to compute the material orientation. And in fact, this is one of the 3 ways that you can compute the material orientation. You can scatter particles in every direction and track the one that travels the longest. And that's roughly aligned with your local material orientation. And even a more recent application is actually the dendrite growth in lithium metal batteries. We have used the Puma particle method to basically do an opposite type of phenomenon than oxidation, where you're actually depositing particles as you go. And that actually, by tweaking again this sticking probability, we have shown that we can mimic a similar dendrite growth as in real lithium metal batteries. So the software has grown a lot in capabilities, and we've recently also added a module to generate artificial microstructures. So these are some examples of the microstructures that we can create. We can basically scatter spheres throughout the domain, or create periodic foams, as well as like fiber structures, which are of course more relevant to NASA. And then for more of a combustion type of approach, or research, it's really interesting to look at triply periodic minimal surface type of microstructures. And finally, of even more interest to NASA are the woven geometries. So we also added a capability of generating from a woven diagram the weave, an artificial weave. So from here on, I'll jump into the capabilities, the property computation sides that I've implemented. And but I wanted to add this slide to basically introduce the topic of anisotropy, and this anisotropy being carrying out at multiple scales. And so what this means is can be explained by looking at a real tomography weave, which is shown here. And as you can see, like the toes have a very directional pattern. And so this directional pattern influence, of course, the properties, meaning that like in the warp direction, the properties are different than the weft direction than through thickness. And if we zoom into like a subsample toe, we can see that there is porosity going throughout the toes, and this porosity also like varies inside the toe, and this also affects the local properties and the anisotropy of these materials. And actually, we have through a research of ours, we've recently discovered that we can track this anisotropy also all the way down to the fiber level, and these fibers are basically made of cylindrical graphene sheets, and so like of course like along the fibers there will be a lot higher conductivity, for example, than across it. And we basically like researched this behavior, and we could see that it matched experiments we could make experiments only by imposing this different fiber conductivity. So at a high level, the next few slides that I'm going to talk about is the material orientation, which is of course critical for considering this anisotropy inside the materials. And then I'll introduce the conductivity numerical method that allowed us to compute the conductivity, including this anisotropic, like considering anisotropic phases. Similarly, here are some of the snapshots of the verification campaign that we did for the elasticity. So the elasticity actually is we could use a very similar numerical method, but basically generalized to vectors instead of scalars for temperatures. So we extended temperatures to displacements. And finally, also through the collaboration with UFF, we have added the effective permeability to PUMA. And so we use a different numerical method for this, which is based on finite elements instead of finite volume. But we still like basically optimized it as much as we could for these voxel meshes that we're getting from tomography. So starting from the orientation methods, there are 3 different functions that we've implemented. The first one is we call a structure tensor, and it's basically based on an image processing technique called the structure tensor, which looks directly at the grayscale values of your tomographic domains, and it picks out by applying different Gaussian blurs and derivative of Gaussian filters. We can basically pick out, and doing an eigenvalue analysis on these filters, we can basically pick out the direction along which the gradient of these grayscales changes the least. And this turns out to be a very good estimate of the local orientation of our fibers. Similarly, we also implement using the conductivity solver. We basically added an orientation method, basically by imposing an artificial conductivity of 0 to the void phase and of 1 to the solid phase. We basically run conductivity simulations in a specific direction, and the heat fluxes that are generated, which were shown like at the end of the simulation after the solver has converged, the heat fluxes are going to be roughly aligned with your local orientation of the material as well. And then finally, this is the raycasting, which uses the particle method that I mentioned earlier, where you track the longest traveling particle and pick that to be your local approximate orientation. So we've wrapped up this work into a part 1 paper to computational material science. The part 2 actually was about the conductivity, which uses the local orientation of these phases. So in this slide, I'm gonna basically talk about the conductivity and elasticity numerical methods that we use, and this is because, as I mentioned, they're solving very similar governing equations, and so we could use a very similar approach, except that the one for the elasticity is a generalization of the conductivity one. So for conductivity, what we're solving for is the divergence of the fluxes going to zero, which is true at steady state. So we can express these conductivities. Basically, the conductivity are tensors, a 3x3 tensor in 3D. Similarly, on the elasticity side, we're solving the divergence of the stresses going to zero, which is true at steady state. And again, we can relate the stresses to the strains through this elasticity tensor C. And similarly here, we can relate the fluxes to the temperatures, the gradient of the temperatures through this conductivity tensor, except that for the elasticity, it's a 6x6 tensor. Next, so what we are using for the conductivity, for the local discretization of our finite volume scheme, is called the multi-point flux approximation, or MPFA, which is a pretty commonly used numerical method. And this linearly approximates the fluxes to the local nodal display, to the local nodal temperatures through a transmissibility matrix E. And so on the right-hand side, instead, is a multi-point stress approximation, which does the same between the stresses and the nodal displacements through a transmissibility matrix again. So if I blow out basically the mesh in 2D and in 3D, what I'm showing here is basically the nodal values that I'm denoting here with an N are basically the nodes that are cell-centered in your mesh, in your voxel mesh. And what basically the MPFA or MPSA methods are consider is the interaction between different neighboring pixels or voxels in 3D through the blue box is called the interaction volume. So what we are introducing is gradients between these nodal values for the displacements and the temperatures. But at a high level, what we're solving for is basically a boundary value problem, where we are imposing a temperature gradient for the conductivity by holding basically the two surfaces across a domain. And in this case, I just have a cylinder, which could be a fiber, if you will. By holding these two surfaces at different temperatures, and you create basically this temperature gradient. And similarly, for the for the elasticity, we are actually holding a displacement. We're imposing a unit displacement in the 3 Cartesian directions. Except that for the elasticity, we also have to include the shear cases in order to get back the 6x6 tensor. So once you solve and converge the local temperatures throughout your domain, what you get out of the conductivity function is a temperature field as well as a flux field. From this for the elasticity is instead basically a displacement field as well as a stress field. We use these converged fluxes and displacements to compute back and to basically average out the effective property, the conductivity on the left and the elasticity on the right. And this gives us back basically just a column of our tensor. If we repeat throughout imposing these boundary conditions in the 3 Cartesian domain directions, we can get the other basically the 3 columns for X, Y, and Z. And finally, for the elasticity, we also have to impose boundary conditions to impose the shear cases, and which can be computed slightly differently, but this is basically the same approach to get the 4th column of your 6x6 tensor. So the validation of these solvers was basically was performed on different woven domains, and these are different candidates for a project called ADEPT, which is a deployable type of heat shield design. And these are basically the weaves, the TPS weaves that were some of the candidates. And these are real tomography of tomographic reconstructions of them. And as you can see, they're actually like segmented already into by assigning a single ID to each one of the toes of your weave. So what we did is basically the process goes that you want to have, if you have a periodic domain, you want to crop out what is called a unit cell, which is basically the smallest part of your domain that repeats itself. And then once you have that unit cell, you can compute the conductivity or the elasticity in the three Cartesian components by imposing the boundary conditions that I mentioned earlier. And so these are some type the temperature and flux fields that we got out of imposing a simulation in the y direction, for example. If you want to learn more about like the whole validation campaign on this numerical method, on this numerical conductivity solver, we also have a part 2 to the Computational Material Science journal. On the elasticity solver instead, we decided to go a slightly different route, where we analyzed a woven composite at different scales, but each one of these scales is basically artificially generated. So what I mean by that is that, for example, this is again of very relevance to NASA. We have the porous phenolic resin that infuses the weave, and as well as at the scale up, basically we considered the fiber packing, which is the interaction between this phenolic resin and the carbon fibers. And then finally, we use these properties into an actual woven unit cell of the toes and the phenolic phase for the basically the void space. So we also did some parametric studies on the porosity of this phenolic resin and how the elasticity varies according to this porosity, as well as how the elasticity varies according to the fiber packing. And finally, these are the results of an artificially generated unit cell using the properties that we've computed at the matrix scale and the fiber packing. So finally, the last solver that I'm going to talk about is the permeability, and this is actually like chronological according to what was added the last. This permeability solver solves Stokes flow, which basically is valid at very low Reynolds numbers. And we use a finite element a scheme, which is based on a Q1 discretization, which basically means that we're using first order elements in both the velocity and the pressure. And so the governing equations can be written out like this for Stokes flow. And there are actually different approaches that can be taken by imposing the boundary conditions. You can either impose a pressure gradient, or you can impose a force, a body force. The latter is actually more benign towards periodic boundary conditions that you can apply. So this is what we implemented together, again, with the collaboration with UFF. And these are some of we've recently submitted a paper to also Computational Material Science on this numerical solver, as well as the validation campaign. This was actually implemented on through an NVIDIA kernel. Pedro knows all about this, and the validation campaign that we ran on Fiberform is shown here for 3 different samples. We also had like experimental values for similar for a similar type of microstructure. So these are some of the results that we obtained, where you can, starting from the middle, this is what basically the Puma function, or this GPU implementation gives you back, which is a pressure field and a velocity field. And then from these, you can obtain actually you can backtrack the permeability, the effective permeability. And so the results on fiber form look as follow, where the horizontal values are the in-plane and through thickness. Actually, fiber form has a preferential alignment of the fibers. So that's why we call them like in-plane, the in-plane direction, and the through thickness basically is different because of this alignment of the fibers. And we can see that the numerical values that we obtained actually like aligned with the trend of this through thickness and in-plane components pretty well. So this is the last study that I'm gonna discuss, and it's about the 4D tomography that I also briefly showed earlier. What this effort is about is basically tracking the oxidation of fiber form real time for a real domain, and this can only be done using a very high frequency scanner, tomography scanner. Which is actually at the Swiss light source in Switzerland. So here is a paper that is currently in preparation about the analysis of these data sets, which are terabytes and terabytes of data. And these are basically the results of this getting the tomographic scans and plotting them as they evolve in time. So they also had basically a lamp, which is how they heated up the surface of these materials, and they basically could also flow different pressures of air through the samples, and this is how they controlled the different and created basically the different environments. If I show these videos again, you can see the surface recessing in different ways, and actually here it just collapses because it oxidizes in the depth until basically the material becomes very brittle and it just collapses at a certain point. So what I actually worked on was the analysis that we did with Puma, and we wanted to basically explore how the properties change throughout the depth and throughout time, basically. And what we did was I'm plotting here basically the same fiber form samples, but tilted horizontally. And we considered basically a convolving filter, where we just compute the material properties for a specific chunk of material, and then we move it by whatever amount of it's actually 50 voxels in the depth, and recompute again the properties for that chunk, etc. And until you do this process throughout the thickness, and then also throughout time. These are the results, which are actually which I obtained very, very recently. We ran this study for conductivity, permeability, and tortuosity. And what you can see here is basically the two rows correspond to the through thickness components of the material properties, and the in-plane is below. And we also ran a similar study for the fiber orientation, where we keep computing the fiber orientation throughout time, and we basically can track how the fiber elevation changes as the material oxidizes. And of course, you can see pretty clearly that there is a correlation between your material properties and the fiber orientation that is changing. But it's very interesting to see that we can capture, for example, the fiber compacting as they collapse with each other, and this is basically when you see these bright colors, that's what is happening. Or you can see the fiber pull up, which is basically these bright colors for the orientation. And I mean, there's a lot to talk about on these graphs, but this is I want to wrap it up here. And I thank you very much for listening, and I'm happy to answer any questions that you might have.
Hi, Federico. Thank you very much for your presentation. If anyone has question, please just type in the commenter in the chat that I can reply here to Federico. Federico, it's very impressive, yeah, the images, the models, yeah, and they get very educational and illustrative, and I think that's pretty much thanks to Puma, yeah, and your efforts to develop even further Puma to allow this very, very comprehensive study of material microstructure, yeah. How long are you working with Puma, Federico?
How long have I been working for?
Yes. When did you
So 5 years now. This is my fifth year at NASA, and I've basically dedicated my life to Puma for the past 5 years. But yeah, we really tried to make it as user friendly and as comprehensive. We really wanted to create like a framework that would be the go-to framework to analyze tomographic reconstructions. And I mean, at NASA at least, like it has had a lot of success in terms of like analyzing different type of weaves or different types of carbon fiber TPS. So I'm really happy about the response of and the use of my software so far.
I have a last question. Can you track more or less the people that are using Puma? How's the feedback you have from the research or industry community that uses? Can you talk a little bit for us?
Yeah. So basically, it actually used to be simpler to track the use of Puma, just because it used to be export controlled until like a few months, until about a year ago. So basically, we could back then, when it was export controlled, every time a user wanted to have access to the software, he would have to go through a NASA process to get access to the source code. And so like until it was actually open sourced, we had I think it was about like 150 users of the software that had gone through this process of requesting the source code. But since like it got open sourced, and since it's on GitHub for anyone that wants to use it, we try to and actually like you can track the Conda installations that the software gets. However, like we think that it's actually like a lot of like internet scrapes, because we're getting like thousands of Conda installations, and I think that's incorrect. So I would say the number of users as a very like low estimate is at least 150 people that have at least tried the software and installed it and used it for a few analyses. But in terms of it's very hard to say how many it is since it's gone open source. So yeah.
Thank you again, Federico. We didn't receive until now any question, but I always tell if anyone is interested in the work of Federico, feel free to contact him. I think it's easy to contact him. And again, thank you very much for coming here, for presenting your research works. It's a very intensive computing work. It's very nice to see computing numerical methods using real life and very important problems of interest, and really pushing advancing the techniques that we work. It's really, really nice, Federico. Thank you very much again.
Thank you for having me.
Bye-bye.
Bye.